For everyone following along, I know there have been some prior modules, and there is a Google Drive. So this module will be module 5. So if you go to the shared Google Drive and go to module 5, you'll see the resources there. And I know there are instructions in the README of how to copy these files into your personal drive. So we're going to start with some slides to give everyone context. So you can follow along in the PDF, and I'll also be sharing my screen. So I'm going to be talking today about how you can practically leverage large language models, or LLMs, and retrieval augmented generation for your work in physics. And I previously was a grad student at Brown. I graduated with my PhD in 2016, and I've been working in industry at LinkedIn ever since, where I use AI and ML. So first, I'd like to thank a few folks that have contributed. So Chong Wen at Brown put in a lot of work testing and contributing to the notebooks I'm going to walk through today, and provided a lot of helpful feedback in making sure they work. Ariel helped coordinate the workshop and get everything in order for today. And then, of course, Rick and Jan as the faculty organizers for the workshop. Thanks for both organizing and for the invitation to present today. So a little bit more about my background. As I mentioned, I was a grad student at Brown. I was there from 2009 to 2016. And I spent my time working in Rick Gateskill's group, looking for dark matter. And that photo on the left is one of my favorites. That was taken in 2013, a mile underground near our dark matter experiment. And I had just moved a lot of calibration equipment for my thesis work underground and assembled it. And one thing I particularly like in this photo is if you're familiar with experimental physics work and working in labs, I'm sure many of you are. You can see, the happy grad student that just assembled his equipment, and behind him is the concerned environmental health and safety director, making sure that everything I just moved underground isn't too dangerous. So a few years later, in the photo in the top right, this was shortly before I graduated. You can see Rick and a subset of his group at the time. And for those in Providence, you're probably familiar with this view. This is the top of the physics building, Barrison Holly. And you can see it's a nice fall day in Providence. And at the end of 2016, I moved to the San Francisco Bay Area and have been working, as I mentioned, at LinkedIn in the anti-abuse and trust domain. So the team I'm on for the past 8 years, we build AI models to detect and prevent abuse on LinkedIn. So this could be things like finding and removing fake accounts, preventing your account from being hacked, or fixing it if it did, in the rare case it was hacked. It could be moderating content in the feed that violates policies. We also cover a lot of other types of abuse, like abusive automated activity like spam or data scraping. So you might say, how did I get from physics to doing AI for trust and anti-abuse in industry? And actually, it's not as big of a change as some may think. So back in the physics world, we were building big detectors running them for a year looking for dark matter. You'd have hundreds of millions or more background events, and you were looking for just a handful of signal events. And then, of course, we wrote software to analyze the data. We used optimization techniques like likelihood and some techniques related to machine learning to produce our results. And in the abuse case, on a big professional network, there are some similarities. So looking for a few WIMP dark matter events in your data set of hundreds of millions of background events is very similar to looking for a small number of fake accounts and abusive behavior in a big ocean of normal user behavior on a professional network. So there's a lot, conceptually, there's some similarities, and there's some similarities in the type of techniques we use. So I found the transition to be one that I was well suited for, and I think physicists have a lot to offer in industry, in machine learning, AI, data science, and engineering. So what will you learn in this workshop today? So it's meant to be very practical. So the first thing is we're going to have two notebooks, two Google Colab notebooks. The first of which will go through using OpenAI models via the OpenAI API. And the second of which will show you how to use Meta's open source Llama LLM running locally in your Colab notebook on a GPU. So due to the realities of LLMs, some of this can be done using free accounts from OpenAI, and some of it will require actually funding an account if you want to follow along in those parts. And the second thing we're going to focus on today is how to enable that LLM to answer technical domain-specific questions about, for example, physics research, leveraging physics papers, analyses, documents, and theses. So these are questions that maybe if you just went to ChatGPT and asked, it wouldn't be able to answer because it wasn't trained with that information. Maybe that information is private. Maybe that information has come out a bit later before the model or after the model was trained. But there's ways to supplement and provide that information so that you can actually get responses back from the model that are relevant to you and relevant to your research. So what will we not cover today? So we're not going to cover the foundational concepts behind LLMs and how to train them. That's a huge topic that could easily be its own workshop. And I recommend the following resources for self-study. So these are really great. They will provide a great overview of how these LLMs are created and trained, and what are the concepts that are relevant to understanding how they work. So there's a few videos, just a few hours of your time. You can get an overview, and also that second video is actually very hands-on and allows you to actually build one in a notebook. And there's some papers, the Llama papers in particular are very good overviews of how these models are created. So to start off, we can look at a very simple case about how LLM chats work. So this is something I think many of you are probably familiar with. You've probably used ChatGPT and other chat bots. So how does that work at a high conceptual level? And in particular, an LLM itself is stateless. So the LLM, after the training process and fine-tuning, is a big collection of billions or tens of billions or more of weights that have been fixed, and you can and basically you can put queries into that model, and it will come back with a fancy autocomplete essentially. However, if you just have the model bundle, it doesn't remember one query to the next and what the history has been. So in this example, let's say there's two queries and time is, going down along the y-axis here. The first is you give the LLM your name, it'll respond with a reasonable response. However, if you ask in the next query, what's my name, it won't know. Um, so the way that these chatbot services have uh, worked around this is that there's a client layer that provides a memory of the history. So that's represented by this blue box here. And basically, this client layer records all the prior interactions between you and the LLM. And then for every future question from the user, all of the prior chat history is also provided to the LLM. So in this case, you can provide it with your name, it'll give a good response. And then when you ask another question, what is my name, it'll be able to leverage that prior history that went into the LLM and answer the question. So basically, this is a memory buffer that is provided via the client layer for the chat. So there's a limitation though in the LLM itself, which is the context window. And this is fixed during the training process. It's kind of a design choice when you're creating the LLM and training it. So the LLM processes all tokens in your input prompt up to this maximum context length. So basically, if you have too long of a chat history, you'll need to either, your client will either need to truncate it or have some advanced techniques for summarizing what the prior history has been, and then only passing in that summarized history into the LLM. So in practice, these context windows are getting longer and longer. Early models were order of 1,000 tokens, but now we see, tens of thousands, hundreds of thousands, and even order of, millions of tokens that can be passed into the LLM model bundle. So that's how the chat functionality you may be familiar with works at a high level. But for this workshop, we want to learn how we can make really domain-specific queries about your physics research. And given that LLMs are trained using the data that was available at the time of training, and maybe your private experimental or your research group data may not be available for these LLMs, or maybe there's new research that wasn't available at the time the LLM was trained. We want to know, how can you enable your LLM to answer technical, domain-specific questions about your research, leveraging these resources, these papers, internal analyses, documents, theses. So you might think, hey, well, can't we just pass all of this context into the LLM like a chat? So basically, in this case, you would provide all the text. Maybe you could copy and paste, or maybe it's a more sophisticated system where you put the text of your papers, theses, internal notes into the LLM chat before you ask your question. And this can work. But as I mentioned, context windows are typically, up to 10 to the 5, maybe 10 to the 6 tokens currently. So even at these limits, maybe it's between 100 and 1,000 pages of human text. So if you want a big library of theses, which as graduate students, can be pretty long, you're probably not going to be able to put that all into a context window. Now, this is getting better, and the windows are getting larger, and summarization techniques are improving. So this is definitely a way forward, but there are limitations in terms of cost and of course the amount of data you can put in this way. So there's another solution though. And that is retrieval augmented generation, or RAG. And this is what we're going to be focusing on in some of our notebooks today. So RAG functions in a series of steps. And the first step is that you have a big library of internal documents, and you chunk them into chunks of maybe a few hundred to 1,000 tokens for each chunk. And for each chunk, then you create an embedding using a embedding model. And this is something you can create yourself, or more likely you're going to use an open source embedding model. And what that embedding model does is it maps the human language text into uh, into a vector of numbers. So it's just an array of numbers. And what that vector represents is the location of that text in a hyperdimensional space. So you go from human text to a vector of numbers, and the position of that vector in this hyperdimensional space contains information about the content of the original text. So basically, very simply, it's just text mapping of text to a vector, a numerical vector. And for every chunk in your internal documents, you have a point in this hyperdimensional vector space. And there's some nice properties about embeddings depending on how you create them, where similar pieces of text will show up at similar locations in your embedding space. So there's lots of different embedding models, but at a high level, this is what's happening. So this step one in RAG is you take the internal documents, chunk them into small chunks, create an embedding for each chunk, and then put them into a vector database. And what's a vector database? Well, it's just a database that is good at storing vectors of numbers and doing vector operations, things like dot products, which are important, as you know, for calculating the similarity between vectors. So the first step is you load your entire library of documents into the vector database. The second step is you as a user want to ask a query of your LLM and RAG system. So you come and you write a human language query, and you say, hey, what is this number in my, or what is this, what's the answer to this physics question that requires these internal documents I've provided? Your query is passed through the same embedding model. So your query gets turned into a vector of numbers, and it is compared against all of the vectors in your vector database from your internal documents. And the RAG system finds the chunks from your internal documents that are most similar to your query. So what that means is, let's find the chunks from our internal documents that are most relevant based on similar content to our input user query. And the top n chunks, it's a parameter. So let's say the top, you say n is 5. The top 5 chunks from your internal documents that are relevant to your user query are then provided. So now you know, of all of the information in my documents, what pieces of text are most relevant for the query that I just asked. And then the third step in the RAG system is combining the original user query and this relevant context that was found from your internal documents into a single prompt that then goes to your LLM. And the LLM can then leverage these chunks of text from your document library to help better answer the query that you asked. And then it provides a good answer. So in a concrete case, the internal documents are papers, theses, design docs that may be, on your research group's internal systems. And then you're able to leverage an open LLM, like either using OpenAI or using an open source Llama model to actually answer questions about your research that otherwise it wouldn't be able to do. Are there any questions in the chat? I just want to take a pause now to see if anyone has any questions on this. It sounds like no questions. Okay, so
James, somebody just added a question. What is a token?
What is a token? Yeah, so the token is a mapping from, in this case, it'd be from human language. Let's say it's from English to a integer representation of that can be absorbed, that can be used in the LLM. So basically, in practice, it's a parameter that's chosen when you train your LLM. And it's basically going from, it translates maybe a few characters of human language into a single representation that then can be passed into your LLM. So it's usually maybe 3 to 4 characters of human language gets translated into one token. So it's just segmentation of sentences. Okay.
We're good at that point. Let's keep moving. Yeah.
Okay, sounds good. One sec. Okay. Yeah, so this outlines the RAG process. So at this point, I think it'd be good to transition into the actual notebooks and the exercises we'll work on today. So if I assume at this point you've copied over the notebooks. There's 2. There's one that is Llama. It's a Llama notebook, and there's one that's OpenAI. We're going to start with the OpenAI notebook today. So if you run it in your personal workspace, you should open it up, and there's some prerequisites we need to do before we can start executing. So the first thing you need to do, if you don't have one, is create an OpenAI account for API access. And you can do this at the platform.openai.com here. So if you, so I already have one, but if you go to that link, it'll give you the option to sign up. So let's take a minute for everyone to go and sign up if you have not already. And basically, it should be a simple, let's see if it should be a simple process where you just, use the sign up here. And once you sign in to your OpenAI account, we're going to need to create some API. We're going to need to create some API keys. So the way to do that is go to Settings. And one of the API keys we need is an organization ID. So that is available here. And you can just copy it. And we'll do that a bit later, but one of those is already fixed for you. And the other, you're going to need to go to the API keys page and create a new key. So you can, I'm not going to do this now, but basically you can create a new key here. Let's actually, I can say example. You can have a default project and then you create your secret key. This one is shown here. I'm going to delete it right after this, but this is the key. You can copy it. You would not delete it, but you'd save it here. And this will be used for the API access. So at this stage, once you have your API keys, part of this notebook, you're going to be able to run using a free account. If you want to complete all of the exercises in this notebook, you are going to need to fund your OpenAI account for larger API calls. $1 should be enough. So it's pretty inexpensive. But basically to use the number of tokens we're going to need to run some of these examples, you need to actually fund it. And the way you do that is you go to billing and you can add a payment method and add to your balance basically. So that's an option. You don't have to for the workshop, but if you want to follow along for the full notebook, you'll need to do that. Are there any questions at this point on setting up the OpenAI notebook and getting the OpenAI account working? Sounds like people have it well in hand. So the
James,
yep.
so sorry, we are getting a number of questions saying, could you please repeat the process? I think it is sufficiently challenging.
Yep.
So
Yeah.
I think I hope we've got time. I think we have time. If you just literally very beginning of the getting how to link into OpenAI, there are a few people who I think it caught them by surprise. They were still getting their notebook in order.
Absolutely, yeah. This is expected. So, yeah. So the OpenAI process is first you need to create your OpenAI account. So you can follow this link, and create an account with an email, and you'll provide a password, and that's at platform.openai.com. And once you have your OpenAI account created, you're going to need to create some API keys. So the way you do that is you go to settings, the gear icon up here. And the first API key is already provided to you. That's the organization ID, and you can copy this. And then the other API keys are shown in the API key page here. And the way you create them is you just create a new secret key and you fill out this form, select default project, name your key, and create the secret key. So again, we can say example, create secret key. You're going to want to copy this key. It's critical to copy this at this point. So you can just press copy. And basically, do not share this. I'm going to delete it right after this, but do not share this because people will get access to your account using this to make API queries. So you copy this key, and that'll be used later on in your notebook. So the secret key here, your secret keys are then shown here that have access to your OpenAI account to make queries, and you can manage them here, including delete them, which I'm about to do. But make sure you copy the key during that creation process because you can't see it again. So I just revoked the key, which means no one can use that key to make queries against my account. So if so hopefully that helps folks go through the steps to create these keys. And as I mentioned, you're going to need to use them in your notebook. So the way we are going to do that is we're going to create secret variables, which are like environmental variables for your notebook. So the first one is that organization key, which was, if you recall, you can see it in the gear, your organization ID. Yours will be different than mine. So, copy yours. And you're going to want to take that organization ID and define an environmental variable called OpenAI organization. The way you do that is you go to this key in your notebook. It's called secrets. And you just add a new secret and you call it OpenAI organization. So, add new secret, and then you can just name it. And in your case, it'll be OpenAI organization, and then you paste in the value here, and that's all you have to do. So the second key is that private API key that's created here, that you copied when you create it. And for that one, we're going to call that OpenAI API key. And similarly, I have already added mine to the notebook for my Google Drive. And you just go to secrets and name it OpenAI API key and paste in the value here. And basically, we'll show a little bit later on how your notebook accesses these API keys in the secrets. And one of the things that's nice about the Google Collab is that your secrets are private to your Google account. So others that you share your notebook with do not see these secrets. So this allows you to put in your keys or passwords here and not have them explicitly written out in your code. And I'll show you how to access those a little bit later. Are there any other questions on this process, or do folks feel they have it in hand?
Looks like we're good now.
Excellent. And again, the first half of this notebook can be completed using a free account. The second half will require funding your OpenAI account with order of $1. You could put in a few dollars, and you can do that here with billing. So you can add a little bit of credit. You'll have to add a credit card to do that, or another payment method. And it should be inexpensive for this demo. So now we can start to execute the notebook. So the first, so we're just going to walk through some of this execution. I'll describe what's happening in each one. So the first is kind of just some boilerplate that I like to use that helps format outputs in Python notebooks. And the next thing we're going to do is install the packages that are required for OpenAI access and creating the RAG, the retrieval augmented generation, using Llama, a tool called Llama Index. So the way we install those in our OpenAI Google Colab notebook is using pip install. And basically this should only take a few seconds. And one of the things I like to note is that I've specified the exact versions of each dependency here. And I'd suggest, here, but also generally that's good practice, because this ensures that in the future, even if there are newer versions, pip grabs the versions that work together for the analysis you've done. So it makes your work more reproducible, and it ensures that in the future, if these pip libraries are updated from the library owners, that you're still pulling the older version that you knew worked for your analysis. So in general, this is good practice. So you can see we've done that. And that enables us to now import the libraries and capabilities that we need. So we import the OpenAI module and some methods from Llama Index. And this should just run in a second or two. And this next step is where you use your OpenAI keys. So in this case, and this is how you grab them from your secrets tab. So as you remember, we created these secrets called OpenAI key and OpenAI organization, and you pasted in the values from your OpenAI account that we created. And this allows you to actually get those keys and assign them to variables in your notebook, and then you can actually use those values in your code. So we run that, and it's going to ask you if your notebook can have access to those secrets that you've defined, and you just grant access. And then you've assigned the organization and API key for OpenAI API access once that runs. So any questions regarding this process so far?
No new ones.
Thank you. So the next step is we start to get into the fun part. So this is where we're going to ask some physics questions of our GPT, our OpenAI model. And I've defined a handful of them here that we're going to use for our analysis. And feel free to ask other questions. You can define a 6, a 7, an 8 with your own questions. Any arbitrary questions you want to ask ChatGPT through the API or GPT through the API. But the 1 through 5 here are the key ones that are going to be used for the demonstration today. And these questions are physics-specific questions that the model would not do a great job of answering without really specific resources that are made available to it in terms of papers and theses. So this is about the dark matter research from around the time of my PhD work in 2016 or earlier. And basically, I've defined a few questions that are, we'll first test them with the OpenAI model with no rag, and then we'll test them after supplying the required physics papers and theses to answer them, and you'll see the difference. So if you run this cell, you can see you'll just create this questions map with the questions we're going to ask. And this next section is defining a kind of a simple function here, which will allow us to use that OpenAI library to access access the OpenAI API put in queries and get the OpenAI model's response. So, typically you'd be familiar with just going to a web UI for ChatGPT, pasting your question, and it will respond back with an answer. This will allow you to do it programmatically in your notebook. And it's pretty simple, as you can see. We assign the API key here, and then this client object is used inside this method where we define some parameter for messages, which is the question you ask. And we also specify the model we want to use. So for this example, we're going to use GPT 4.0 mini. And there's a lot of models available. We're not going to go through all of them now, but you can see them actually if you go to this OpenAI limits page. You can see all of the models. So we're going to use this 4.0 mini. 4.0 mini. There's some parameters around token limits, request limits for that you can see for the different models. Obviously, the different models have different levels of performance in terms of the quality of their responses. 4.0 mini is one of the newer and better ones. And there's actually a ton of models that OpenAI makes available for you for different purposes that you can access via API. So all the names and the limits are shown here.
James, sorry, it's Rick here.
Yes.
I did have one request. I think some people wanted you to make the font a bit bigger, if there's any chance. Maybe.
Yep. Zoom in even more here, yeah. How's this?
Tremendous. Thank you, sir.
Got it. Okay. And so by running this, it's just defining this method query OAI, which allows you to, again, take in a question and return the completion. So that was very simple. And at this point, you should be able to actually take one of the questions and pass it into this method and get a response from OpenAI. So in the notebooks I provided, I had already run all of the examples. Just for folks that run into issues, you can still see the output. Or maybe if you only want to follow along a certain amount, due to using a free account, you can actually see all of the outputs, even in the later parts of the worksheet. But at this point, we are going to rerun all these cells one by one and take a look at the output. So if we run this, what's happening now is we defined that question, the first question here in this question 1, and it is passed into this query OpenAI method, and we get the response, and then there's some code here to print the response and extract the message content. So for this first question, we asked, hey, in the Lux DD analysis, which was a big part of my thesis back when I was at Brown, what neutron source rate provided the optimal match between the absolute number of single scatter events and simulation and data? So basically, I was asking, there was some part of the analysis in my thesis and some of the papers we wrote. What was the neutron source rate that we used there to match simulation and data? So obviously, this is very domain specific. And you can see that OpenAI comes back with a response. It does know about the LUX, the Large Underground Xenon Dark Matter Experiment. And it sounds pretty authoritative. It comes back and it says, hey, the optimal neutron source rate is matching simulation data was determined to be 0.8 hertz. This rate was used to calibrate the response to neutron interactions, which is critical for accurately interpreting data in searches for dark matter. So this response is absolutely correct, except for this neutron source rate of 0.8 hertz is complete nonsense. So it sounds right, but the numerical value, the actual important detail here, the important information is wrong. But you could, so this is, there's maybe a few conclusions here. One, the OpenAI model doesn't have the information at its fingertips to answer the question correctly. So that's one conclusion. So that's one thing we're going to want to fix later on. But the second conclusion I think that you can draw is that even if it doesn't have the information, it will respond authoritatively and basically in this case it's you may be familiar with the term hallucination. The model will authoritatively respond with wrong information. And in this case it's a little confusing because this response is all correct qualitatively, but the quantitative detail is wrong. Were folks able to run this using your OpenAI key, or are folks having trouble at this point?
Based on the feedback, I think people are running okay. One or two people have hit things like rate limit error. Okay, one or two people are reporting rate limit errors. I think you were saying the way to cure that is, unfortunately, well, is to provide a tier one, to go to the $1 level.
Yeah, I think you've got to go to the $1 level, which will upgrade your account from a tier 0 to a tier 1. Yeah. But if you're not able to fund your account now, you can of course follow along, and all the responses are already in the notebook, so you should be able to follow follow along locally and look ahead as well.
Just add, when James was preparing this, we looked, and Chong Wen as well, we all looked at this issue of how to interact with LLMs. One of the lessons that we certainly got during the months, preparing, was realization LLMs are a big consumer of CPU, and the free model rapidly disappears with LLM. It's still incredibly low cost. But you do have to be ready to spend, I'm afraid, at the sort of, tens of cents level, which means getting a credit card or some billing system going with OpenAI. So we do apologize for this, but we looked at this very seriously, and there was simply no way to interact with LLMs that were the kind of level of sophistication that are necessary for the answers to be well constructed. Yeah. Anyway, thanks, James.
Yep. Thank you. Thank you, Rick. So at this point, let's go through the other 5 questions, the remaining of the 5, and investigate their outputs and see what patterns we see. So we can very simply, now that we've set up all that boilerplate and funded our account, we can very quickly ask other questions of the model. So here we ask the question in the first results from the Lux detector. So these are published papers back from early in the 2010s. What was the average electric field used when measuring the charge in the light yields? So the response is, again, qualitatively right. It gets the qualitative physics right here, where it talks about the average electric field in the detector was 0.25 kilovolts per centimeter. This setup allowed researchers to investigate the properties of dark matter interactions in xenon, focusing on scintillation and ionization produced from interactions. So all of that is qualitatively right, but again, it's getting the quantitative details wrong, and you wouldn't know it just by looking at this response. So very similar to the first question in that case. We can then go on to the third question we want to ask, which is, what is the mean energy of neutrons produced by a DD-108 fusion source? So this is that equipment that I had that photo of early in the presentation in the slides of me down underground with the shadowy EH&S director. that was a DD-108 fusion source, which was a neutron source. So there is some public information here. So in fact, that is not specific to our experiment. You can go and read about DD sources. So this is something you might expect the model to be able to answer even without specific information about our experiment. And it gets it right. So qualitatively, it talks about the DD fusion reaction, provides some details about the relevant reactions, and then gets the energy right. So it says, hey, it's around 2.5 MeV. It varies slightly, but the average is 2.5 MeV, which is correct. Although, so quantitatively, it's getting the answer right now, but it's not specific, the specific energy that was measured, as we'll see later, for our particular DD-108 source in our model. So this is qualitatively and quantitatively right, but isn't specific to our experiment. So the next question is, let's see, we can run it. And basically, what was the energy at the endpoint of the DD neutron recoil energy spectrum in liquid xenon? So this is basically asking when in our detector, a neutron from this source comes in and hits a xenon atom in our particle detector, our dark matter detector, and that xenon atom recoils. And what is the energy that's imparted onto the xenon atom? And then what is the size of the signals that are the scintillation and ionization signals observed in the detector at that endpoint? So this is qualitatively it's able to describe it right, but quantitatively this is not correct. Order of magnitude actually it's all right, but it's not very specific. And we'll have one additional question, one final question here. And that is, what is the, because this is kind of a different question, it's what's the ER response? So ER is a different type of interaction in our detector, our dark matter detector, where particles interact with the electrons of the xenon atom. This is electron recoil, which is different than the interactions neutrons participate in the detector. And there's a different source here used, which is a radioactive isotope of xenon 120, it's 127. And we're asking, hey, how low in energy did we measure the ER response? And then where did the xenon 127 come from? So OpenAI comes back. As you can see, it's very qualitative. Qualitatively, it's roughly right. Quantitatively, there isn't much detail in the response. It doesn't have the domain-specific knowledge required to answer this concretely based on our experimental literature. So I think at this point, everyone should have been able to run through these questions with their API access. If you needed to fund it, hopefully that's worked for you at this stage. Are there any questions up until this point? Because the next step is particularly exciting because this is where we're going to actually pull in a lot of papers and theses to answer these questions much more quantitatively and correctly. And this is where you'll definitely need to have funded your OpenAI account to proceed. So the first step here is we're going to need to mount. I think in other modules you've likely done this as well. I think in the README there are some directions, but basically we're going to need to use the Google Drive utilities to mount the shared drive here. So it's gonna you're gonna run this and it's gonna ask you to connect to Google Drive. You're gonna agree. There's gonna be some pop-up where you choose your Google account and you're gonna have to press continue a few times to agree to mount it, and that should work for you. And basically, um, let's see, it should take a second or two. Okay, so it ran here successfully. What we're gonna do then is go into the winter school shared drive and take a look at the LuxDD papers that are in the module 5 directory. So if we run those, it lists 2 papers here. And if we go back to our module shared drive, you can see in the documents LuxDD papers, there's 2 papers here that were published back in the 2010s on related to some of this work that we are asking questions about. So was everybody able to mount their drive at this point? I think that should work in a straightforward way.
In many previous modules, and we're not getting any negative feedback on that. There were 1 or 2 questions that came in more recently. Let's see, I'm just trying to ones that make sense. There was a question, let's see, it was a few minutes, yeah, sorry, about 7 minutes ago. Since you are using a temperature of 0.7, does the model make up new wrong numbers each time? Or does the quality?
So there's no temperature specified here. So that's in the Llama model notebook, and we'll get to that a bit later. But for the OpenAI, we're just using the defaults, and I think it's been pretty reproducible. These responses are pretty they do vary a little bit, but they've been pretty. If you run the query multiple times, you can experiment to see if OpenAI comes back with slightly different hallucinations. What I saw during testing these notebooks is that it was actually OpenAI was providing pretty consistent quantitative numbers, albeit wrong numbers. Okay, so at this point you've got your drive mounted, and we're going to set up that RAG system. So if you remember back in our slides, the first step of RAG was to take an internal document corpus, chunk it, create embeddings, and load it into a vector database. And that's what we are going to do here. So it's very simple, and we're using some of the defaults with Llama Index, but basically you just specify your data path in your mounted directory here. You set a few parameters in terms of the chunk size you want to use and the chunk overlap. And what these parameters mean is chunk size is how many tokens do you want to chunk up your documents into. So in this case, we're going to choose 1,000. And the overlap is how much overlap there is across chunks. So, if you have chunk A and chunk B, there's 100 token overlap between those. And that's a parameter which you can adjust. So typical values from this are a few hundred to 1,000 tokens. And then you can specify, we're going to want it for Llama Index, we're going to want to specify again the model. We're going to use the same one, GPT-4o mini. So we'll just run this. This is kind of setting these parameters. And the next step is using Llama Index to read in these parameters, create embeddings, and populate the vector store. And we're kind of using the default Llama Index options for how to do that. So basically, this might take a minute or two, because what's happening as this runs is the code is looking at this LuxDD paper, these two LuxDD papers. It's looking at all the text in these, chunking them into 1,000 token chunks, which again correspond to maybe 2,000 to 3,000 or maybe 3,000 to 4,000 characters each chunk, creating embeddings of that and storing those in the database. So again, this should just take a minute or two here. And right now, yeah, so it runs pretty quickly because we only have 2 documents and they were relatively short. It's maybe, 10 or 20 page papers. But you could imagine having a directory with a lot of documents, long books or theses, and a lot more content and structure in the database of internal documents you want to load in here. Okay, and then the next step is similar to what we did before. We're going to define a simple method for querying our RAG system. So now that we've created our vector store index, we can create a query engine here where we give it a parameter. And this parameter here is the number of relevant chunks you want your RAG system to provide when you ask it a question. So in this case, we're saying whenever we ask a query of our RAG system, find the top 5 chunks from our papers, top 5 text chunks, and pass those into the OpenAI model along with your question. And then those top 5 chunks of text from our paper will, of course, help the OpenAI model answer those questions more accurately. So we'll define this query rag method. And then once we do that, we can start asking questions. So was everybody able to get this far? Are there any people getting stuck in the llama index, setting up llama index?
No questions being flagged at the moment.
Sounds good. Okay, so now we can just start asking questions, and we're going to ask the same questions that we asked before. But now, of course, the model will have the benefit of those 2 papers that have relevant physics domain-specific information. So we can run this, and this will do the RAG process. So in this cell here, we're choosing the question, which is question 1, and then we're just doing the query RAG method. And as you recall, so what's happening there is both steps 2 and 3. So when we query the RAG, we're going back and taking that user query, which is our question. We're finding the top 5 relevant chunks of content from our papers. And then we're constructing the user query plus that relevant context, sending all that information to OpenAI, and then OpenAI is going to be able to come back with a better answer than it was before. So here's the response when we do that. And again, so this is the same question we asked last time. What was the optimal neutron source rate to match simulation and data? And as you can see, it does a much, much better job. So basically, if you recall last time, for question 1, the model said it was 0.8 hertz, a neutron source rate of 0.8 hertz, which was complete nonsense. If you go, now that we've supplemented our created a RAG system with supplemental information, it's able to come back and answer the quantitatively correct number, which is the optimal match was 2.6 times 10 to the 6 neutrons per second, which is in agreement with the independently measured source rate of 2.5 plus or minus 0.3 neutrons per second. So basically, it is not only answering from the information in the paper what the optimal match between simulation and data was. In our paper, we actually quote with an uncertainty the independently measured neutron source rate, and it recognized that, hey, that's relevant too, and it knows enough to say, hey, this is an agreement. So it's able to correctly answer these questions quantitatively and provide a lot of relevant qualitative context that was specific to our papers we provided. So we can move on to the second question. And this was about the electric field. And if you remember before, it hallucinated, I think, 250 volts per centimeter, which was wrong. But now we're able to get the right answer, where it's actually pulling the value from our paper when we ask what the average electric field was, and the correct value is 180 volts per centimeter. So let's see how it does on question 3. So we run question 3, and if you remember before, it gave a lot of context, and it kind of said it was roughly 2.5 MeV, and here it's able to answer the question. It says it's 2.45 MeV, which is the theoretical value that quoted in our paper for our DD108 source. And the next question 4, you remember in this one, it was very qualitative in its response. It said roughly 100 keV, if I recall, which is, order of magnitude correct, but was not specifically the value that we meant, that we quote in our papers. So when you run this question now with the benefit of the RAG and the papers we've provided, it is able to answer this more correctly. So it's able to come back and say, hey, it's 74 keV, and it's a nuclear recoil. And that's correct. So that is the endpoint of the spectrum of neutrons bouncing off xenon nuclei. And and it actually makes an attempt here for the follow-up questions too. But actually, this shows there are still some limitations in the model can still hallucinate. So RAG will not solve all your problems, and in practice requires a lot of tuning, and you still need to be careful. It says the mean S1 signal is 250 or 2,500 photoelectrons. And that's the amount of light sort of detected in our photomultiplier tubes in the experiment. And a raw S2 analysis of 164 PhD was applied. So this is actually not correct. So these numbers are still hallucinations, that it's not answering correctly. So you still need to be careful is the lesson there. And the next question is question 5, which was kind of a different type of physics question that was about that actually is not contained in the papers that we provided to the RAG. So we would expect the model to still get this wrong. And when you run it, that's exactly what we see. So in this case, the RAG comes back, and LLM come back, and they say, we ask a question about the electron recoil response of our detector measured using a radioactive xenon isotope 127. And then we ask, where did this xenon 127 come from? So the model kind of hallucinates and qualitatively comes back talking about xenon 131 metastable, which is qualitatively right. However, this is not the question that we asked. And as I mentioned, we expected it to get this wrong because the Xenon 127 calibration was not in the documents, these LuxDD papers we provided. So we'd expect it to still fail here and hallucinate, and that's what it does. So one of the cool things you can do here with the RAG system is this response that's returned actually has more information than just the the chat response from the model. And you can see that here in this response.metadata. And if you remember, we had specified up above that we wanted to only retrieve the top 5 chunks, the top 5 bits of text from our papers that are most relevant to our question. So you can actually see where those chunks are coming from here using metadata. So you can see for this question it got wrong. It it still found the top 5 most relevant chunks from the 2 papers that were provided, and it tells you what pages what page of those documents that it found those chunks on. And you can actually see the text of those chunks too. So if you do response.source nodes, you can see the actual text. So this is all the text that's actually passed in with your query to ChatGPT. The ChatGPT or the GPT model can sift through to try and find these quantitative numbers. And basically there were five nodes here. So 5 bits of text that were found by our RAG system to be relevant that we pass in. So if you're debugging, hey, why is it getting it wrong? Or you want to actually look at the text, you're able to do that. That was found relevant. So now we want to know, so does this make sense to everyone, or does anybody have questions at this point? Sounds like,
So,
oh, go ahead.
yeah, no, I think these questions are more general than, yeah, carry on.
Got it. So,
No, sorry, there is one that sort of, it was a little while back, but somebody was a little unclear about the chunk size, chunk overlap setting, how that was really going to influence things. But that I realized that is a ways back, obviously.
Yep. So the chunk size determines how much text is in one chunk that is that your model, that your RAG system will find. So there's some trade-offs there. We chose 1,000, so each one of these chunks, you can actually see the chunk now, which is shown the text basically here, right? So this is like one chunk here, which I'm highlighting. So this is a 1,000 1,000 token chunk here. And basically, so you could imagine if you make the chunk size too small, maybe there's surrounding information, maybe it's a paragraph of information, and you will find chunks that are that do not contain the information you need to provide the model to answer. So if you make it too small, like maybe you're not capturing the information in the surrounding text you need for the LLM to find to answer the question correctly. If you make it too large, maybe your similarity is not done. Maybe you're not able to as effectively find the most relevant similar chunks to your query because there's a lot of context, a lot of information in a really large chunk. And the other thing to consider is if you made really, really large chunks, how big is the context window of your LLM? So if the context window of your LLM is small and you're making really big chunks, you may not be able to pass all those chunks in to the LLM in the prompt to the LLM. So there's trade-offs there. it's something you can play around with, but again, typical values are hundreds to 1,000. And you know, I the you can in your notebook experiment with those and see if you get different responses as you vary this setting. The other thing I like to, and then for chunk overlap, uh, this setting is basically, do you have it, are your chunks completely sequential with no overlap, or is there some common text across chunks? This setting is typically maybe 10% of your chunk size. But I think it's less important than the chunk size parameter. And basically that's making sure that there isn't kind of missed uh, missed context due to the fact that if you don't have any overlap at all, it might be that you, due to arbitrary choices of how the chunking happens, you might not have a cohesive chunk of text that is useful to your LLM. So again, you can experiment with it, but it probably won't make too much of a difference for reasonable values here. So okay, so that last query that we ran, as I mentioned, we deliberately asked a question that would not be answered in the documents we provided to the RAG so far. So we expected it to get this wrong. So how can we fix that? So the answer is, of course, add more documents to the RAG that are relevant to answer this question. So that's what we can do here. And basically, we have another directory in our module 5. So there was another directory here called other Brown PA theses. And these are actually longer. These are PhD theses. So these are like, 200, 300, 400 pages that have the information that's relevant to that last question we asked, the question 5. So, and the other thing to point out here is that we're able to add these new documents incrementally to our existing index. So we'll run it. It'll take a few minutes to run. But what's happening here is we've specified this data path to the new files. We again read them in. We parse them and get the new chunks from these documents. And then we insert these chunks into our existing index. So this index is the same index that we had up here. And that's important because you can imagine as your library of documents you care about gets bigger and bigger, the indexing can actually take a long time and it could be expensive. So you're going to want to have a library, a big index, and incrementally add more to it as you do publish new papers, or you're interested in new theses, or there's new analysis documents you want to add that are relevant to your experiment. You can incrementally add them without creating having to recreate the entire index over. So in this case, it only takes a few minutes, but if there was a very large corpus, it could take a long time and be expensive. So the other thing is, it's not shown here, but you can actually save this index to disk and reload it using some simple commands. So let's wait as this continues to index. And once we have added these theses, it takes a little bit longer here because instead of just being 10 or 20 pages long like these papers, these theses are hundreds of pages long. So it'll take a little bit longer to index these. And this is why this incremental indexing is important. While we're waiting for the execution here, are there any questions?
So there was one very general question, but maybe before two rather general questions. Let's see, but there might be possibly one detailed one here. Okay. Do you have an estimate of what percentage of numerical answers become correct after the LLM is augmented with the RAG? Did you in your? I mean, I know we talked about this during preparation, but I think somebody's asked a very good question there, which is how well does this numerical reliability go up?
Yeah, that's a great question, and it for the purpose of this workshop, these are all kind of anecdotal examples. There's a whole field of study and that's quickly evolving in terms of how to evaluate LLMs and their responses and RAG and um, and basically these are kind of simple toy examples, but if you were to productionalize a big system, you'd want to do those evaluations. Um, and you and and basically it's very dependent on how you set up your RAG. So there will be a lot of tuning to get the performance that you want, but it's going to be very dependent on the documents you provide, the types of how many, how diverse, the parameters and the embedding method you choose to use. And there are a lot of more sophisticated things we're not going to cover in terms of how to improve RAG performance even beyond this. So the answer is it kind of depends, but there's a lot of study there. And if you look up resources about evaluation of LLMs and evaluation of RAG, you can find a lot of active research there. But the answer, but the key is don't trust, any individual response, fully. You should definitely be having the human in the loop evaluating it, if you're asking questions of it that are specific. Okay, so we've added those theses, and now we're going to re-ask that question. So that question number 5, which you remember, it got it completely wrong last time. It said, "Hey, how low in energy was the ER response, and where did the Xenon 120 using Xenon 127? Where did the 127 come from?" And it answered a completely different question. It talked about Xenon 131. So you can see now that we've added these additional documents to our RAG, um, the model's able to answer it correctly. So it says the lowest energy ER response measured using 127 reached down to 186 EV, which is correct. That's quantitatively correct. And the xenon 127 present in the liquid xenon originated from cosmogenic activation during its time on the surface before being brought underground. So that's also correct. So it's able to, not only answer quantitatively our question about the xenon 127, how low in energy the response was measured, but also where does this come from? And we can, so this kind of is a demonstration of if there are new documents, you're able to pull them in incrementally and improve your RAG system to answer questions that previously you weren't able to ask the LLM. And if we look at the response metadata, unsurprisingly, it's leveraging those new theses we added in other Brown PA theses. So as you can see, this is Will Taylor's thesis and Dongqing Huang's thesis, which had information about Xenon 127. And previously, these documents were unavailable in the earlier examples, but now the RAG searches through those theses and finds the relevant context with the information required to answer this question. And you can see, as I mentioned, these are, much longer documents. So it's actually sifting through hundreds of pages, finding the right chunks, and then providing those to your LLM query. And similarly, you can actually see, again, the text if we do a search here, you can actually see the text from the theses where it's talking about Xenon 127. And this is where the LLM is able to distill this down into the relevant quantitative information and answer it for you. So at this point, I think each module has a Google form where you can submit an answer. So at this point, we're going to do an exercise. So for everyone that's followed along and added the theses in and set up the RAG systems, if you follow along this far, you should be able to get an answer. I'm not going to run the query here because I don't want to provide the answer, but if you run these final two cells, there's a question that only can be answered if you had set up the RAG and added all the documents. So this is what is the energy of the lowest QY measurement achieved with the DD 2016 calibration data? So, and then how much lower in energy was this than the 2013 Lux QY result? So this is kind of a complex question, right? So it's got to go and understand, hey, there's different charge yield measurements that were done. Quantitatively, it's got to understand there are different calibrations at different times. It's got to understand what the lowest QY or the lowest charge yield point means and pull out the energy. And then it's got to look at a prior calibration in these documents we've provided, and then explain how much lower energy the 2016 measurement was than the 2013 measurement. So go ahead and run these. And then go to I linked it here, but go to the module 5 form and just paste in your answer for the module. And at the end of the section, at the end of this module, we'll take a look at the answers and see if folks were able to get the right answer. And I'll also share the right answer at the end of the session. Okay. Any questions on the OpenAI notebook? Otherwise, we can change gears into the other notebook at this point. Okay, sounds like we're good to change gears. And Rick, just to confirm, I think we have an hour left. Is that right? In the module. Just
Say that again.
Just to confirm, I think the module, the workshop module, we have an hour left just on time. Is that correct?
Past one your time is the end.
One my time, so half an hour left.
No, half past. Sorry, you've got an hour.
Got an hour. Okay, yeah, I got it. 1:30. Okay.
So by the way, somebody has asked, is it possible to get answers without paying the dollar? As I say, we're really sorry. We tried to look for a way of getting LLM compute for free, but one of the things and I tried to type this into the announcement chat as well. You've got to understand these LLMs are computationally beasts. It's not always obvious that you're getting access to so much compute. So getting access to this kind of compute for free is, somebody has to pay the heating bill because the silicon. I think so. We're really sorry. We just have not been able to. The OpenAI pricing was very reasonable, it seemed to us, but I'm afraid the dollar level at the cents and up to sort of a $1 level, we just could not avoid that way. And I'm sorry. Okay, thanks, James.
Yep. And also, even if you're not able to fund the account and run the cells, the notebooks I've provided do have all of the output up through this stage. So if you want to look offline and look at the queries and responses, you should be able to see them and follow along. And the other point to make is it's a good exercise, you know, if in the future your research group wants to use OpenAI programmatically, you know, this is a good example of how to do it, how to set up the API keys, and then maybe your if your research group can fund those types of API calls, then maybe it'll be relevant for you in the future. Okay, so we are going to change gears and go into the second notebook.
James,
So,
I'm so
oh, yep.
we've had a couple of people say they don't quite understand what their organization key is about. Are you able to summarize? I know you covered that. Are you able to just reiterate again, or if it's complicated?
Yeah. So it is it's created when you create your OpenAI account. So if you create your OpenAI account with like a personal account with your personal email, you'll get an organization API key that's unique to you. And you know, so basically you don't need to worry about it too much. You can just copy and paste it in. It matters more is if your organization is has created a bunch of um, you know, if you have a company or maybe your university is paying for a lot of OpenAI accounts, the organization ID would be at the organization level, and then might have specific API keys for specific projects or users. So it's just a way. In this case, it doesn't matter too much. You can just copy and paste it in. But if you have an organization, university, company, employer that is paying an OpenAI contract, then your organization key may become more relevant because everyone will roll up into that key.
Very clear. Okay, we should move on with the science. Yep. Thanks.
Okay. Okay. So the next notebook. Apologies again. This is one where all of the examples are here, and the outputs are here. But again, to actually follow along and run these, you need to fund. In this case, you need to fund your Google Colab. So again, it's optional. We're gonna walk through it, but this is I think very relevant. For researchers. And basically this is going to be following the same structure as what we did with OpenAI, but in this case we're going to be using the Llama notebook. And basically in module 5 there's this Llama Python notebook, and Llama is a an LLM that was created by Meta. So, and they open sourced the weights. So every new release, they actually make the Llama weights available and free to use. So you can actually go download the weights and run them locally on your laptop or your if you have enough RAM, or your you know, your cluster, or in this case, for the purpose of the workshop, we're going to be running it hosted in the Google Colab notebook. But to actually host the Llama model, it's so big, we're actually going to have to pay for the Google Colab Pro to do this. One thing I would like to mention is that you know, for the workshops, we are using Google Colab to make sure that everyone can follow along and share. So that's why we need to pay to host it. You can actually run this Llama model locally on your laptop. We're not going to go into that because that's a little bit more complex, but if you're interested, or maybe for your research or your research group, you want to run an LLM locally, you can actually, if you have for example, a MacBook with the, you know, M1 or better processors and enough RAM to fit the Llama model, you can load it and get good performance on your laptop, or Mac Minis, for example. But here we're gonna run it in Google Colab. So there's some steps here. The first is we have to get access to the Llama model, and these are published as many AI models are these days in a platform called Hugging Face, which is um, available at huggingface.co. And you'll need to create an account here if you want to follow along in detail. So basically, if you go to Hugging Face, I've already signed in, but if you go, there's an option to sign in and you can create your Hugging Face account if you go to huggingface.co. Let me zoom in here. And basically what Hugging Face is a repository. It's kind of like a GitHub, but for models and model weights and data. So people and organizations publish uh, model weights into Hugging Face, and then you can access them and download the weights if you want, and that's what we're going to do. And there's some nice libraries that enable you to do that easily. So go now and sign up at huggingface.co. And once you sign up, you're going to need to request access to Llama. And there's a link, let's see, there's a link here on how to do this. And basically, so I've already done it, so I can't demo it easily here. But basically, if you follow that link, you will see a slightly different page where sort of at the bottom there's a button which will say, hey, file an application for access. And you'll have to give your name, your organization, the country you're based out of, and your role, what you're going to use the model for. And you request access, and within a few minutes, you will get an email saying if you've been granted access, you'll get an email. So it's pretty automated and quick. It may depend on the country you're based in. There may be some that take longer or have trouble, but that'll be a case-by-case basis. But basically, there's some concern about the safety and uses of these big capable AI models. So that's why Meta gates access. So I've been granted access here to this particular llama model. And you can see I have, once you get access, you'll see it on this page here. So again, everyone right now should be signing up for Hugging Face and then going to this link, here to get access to that model. And Llama 3.1 is one of the more recent ones. And basically, these models are huge. So Llama 3.1 comes in 3 sizes. And of course, the bigger the model in terms of the number of weights, the better the performance. But of course, the more resources are required in terms of RAM and GPUs to actually run the model. So Llama 3.1 has 3 sizes of model. There's an 8 billion parameter model, a 70 billion parameter model, and a 405 billion parameter model. For the purpose of this workshop, we're going to use the smallest. So that's the easiest to use, and that's 8 billion parameters. As I mentioned, even with the 8 billion parameter model, we have to pay for upgraded RAM and GPU access in Google Colab to host it. So the hosting requirements, as you can imagine, get more and more complex as you get to the bigger models. So we'll use this smallest one. And one other thing I want to point out as you're going through the sign-up process for Hugging Face and requesting access to Llama, there's actually a lot of Llama models. So basically, Meta continues to publish just like a GitHub repo. There's a lot of contributors and Meta continues to publish many versions of these and associated models. So in fact, there's a Llama 3.3, 3.2. There's prior versions. There's a here's all the llama models. There's llama 2. There's there's some that are fine-tuned for different purposes. So we're just going to use that one that I linked, which was the 3.18 billion instruct. But that should kind of give you a sense of the scope of models that are available on Hugging Face. And this is just llama, but of course there's huge numbers of models that research groups, companies, individuals publish to Hugging Face from all over the world that you can download and access and run locally. So at this point, hopefully everybody's created their Hugging Face account and requested access to Llama. Similar to what we did for OpenAI, you're going to need to create an access token for Hugging Face. So if you go back to our notebook and you click this link to setting, it says settings tokens, you will be directed to your account's user access token page. And all you have to do is go to create new token, and you will see a lot of options. And the key ones that you're going to want, so you're going to want to name the token, and then you're going to want to give access to, read access to all contents of repos under your namespace and contents of all public gated repos you can access. And this one in particular is important because the Llama model is, of course, in that meta public gated repo that you had to request access to. So you're going to create a token here, and then it'll show up here. So you can see I already did this, where I named it the Brown Physics AI Winter Workshop. The value is here. When you create it, again, you need to copy that token because you're going to need to add it to your notebook. And there's some fine-grained permissions here, so you can see, again, it's those first two permissions for the Brown Physics AI Winter Workshop. I don't think any other are required here. It's just these two. So hopefully that makes sense. Again, as you create your token, as we did before for OpenAI, this time you're going to need to add another secret called HF_token, all caps. That is here in our notebook, HF_token. So what you create that Hugging Face token, and then you paste it in to your notebook secrets here. So are there any questions on the Hugging Face platform or the sign up process or the token process at this point?
Don't have any in the chat, in the Q&A at the moment.
Sounds good. And again, to follow along, in this notebook, you really need to, we're going to need to sign up temporarily for this Google Colab Pro. So again, it's optional. All the outputs, you'll be able to follow along. I think this is interesting because even if you don't want to pay later on, you can use these locally on your laptop or on a Mac Mini in your lab. So Llama is relevant from that perspective. So to do this, we are going to click Colab Pro. So this is $10 to sign up for. Again, optional. Apologies, but there's no other way to run these in Google Colab. And then you can sign up here with your Google account. And the one that we would choose is this Colab Pro plan. And the reason we need to do it is it gives access to compute units to make sure that you're able to execute the queries with priority, GPUs that are required for inference, and more memory on those GPUs to fit even the smallest Llama model requires the bigger GPUs to fit it in memory. After signing up for the Google Cloud Pro, we need to actually change our notebook to leverage the advanced capabilities. So the way we do that is we go to runtime, and you go to change runtime type in your notebook. And I've already done it here, but basically I think the default is typically the T4 GPU, but after you sign up for Pro, you can use the fancy NVIDIA A100 GPUs and high RAM. Um, and again, that's required even for the smallest Llama. This is required to run it in the notebook. So we can save that. And now let's start running through. Again, it's optional to go through those steps if you want to pay or not, but otherwise you can just follow along and see how Llama does in comparison to what we were doing with OpenAI. So as we run the notebook, a lot of this should be familiar. We'll start with some, boilerplate for formatting Python notebooks outputs. And then the next thing we're going to do is do a pip install. There's a lot more dependencies this time. We still have Llama Index, but instead of just an OpenAI model, we're going to need to install Hugging Face and some other libraries that are required to create these embeddings for RAG manually. So again, as I recommended before, every dependency, you're assigning the actual versions that work for your notebook. And we're going to do a pip install here, which should only take a few seconds. One thing we will need to do is some of these dependencies are actually, I think, used by the notebook itself. So it's going to come up with a warning that we need to actually restart the notebook after we did this pip install. And that's fine. So we've now installed all these dependencies, but we need to restart the notebook so that the notebook can actually use them. So all you have to do is press restart session, and then you rerun those first two cells again. And this time it'll say, hey, these requirements are all already met, because during that last iteration, we installed them. So it says requirement are already satisfied for everything we need. And then we're going to import all of the Python libraries into our environment that we just installed with pip. And these include Llama Index capabilities for RAG, as well as some additional capabilities required to run Llama that we downloaded from Hugging Face. So at this point, hopefully everyone that wants to follow along has set up their Hugging Face token here in their secrets. And we can log into Hugging Face here. It should work. We just grant access to that token. You can see it now has access, and we're able to log into Hugging Face using our secret token. So the next step is kind of interesting and very different from what we did with OpenAI. So this is where we're going to define the Llama, the parameters for our Llama model and how we're going to use it. So one of the things we're going to do is define a system prompt. So this kind of this comes before the Llama model and tells it what it needs to do, or comes before your prompt to the Llama model and tells it what it needs to do. So here we're telling the Llama model, for every query we send to it, before it gets our query, it hears, you are a Q&A assistant. Your goal is to answer questions as accurately as possible based on the instructions and context provided. So that's text that actually goes to that's kind of the boilerplate inserted at the beginning of your query for every query you send. And there's some other boilerplate that wraps your query here. And this is kind of some default Llama Index a boilerplate text here. So basically, this is just defining these boilerplate prompt strings for Llama Index. This next step is where we actually download Llama, create our tokenizer, and set all the parameters that are required for our Llama model. So this will take a few minutes to do, because even with the smallest llama model of 8 billion parameters, it's still, 15 to 20 gigabytes of data that needs to be downloaded. So that those 8 billion parameters. So these models are huge, and that's why we need the bigger RAM and the GPU to do inference here. So as you can see, it's broken up into 4 chunks. Each is maybe 5 gigabytes, and the system, we're downloading them now into our notebook from Hugging Face. While that happens, I'll talk a little bit about some of these parameters we set. So it's a lot more fine-grained control than what we did for the OpenAI case. We're specifying specifically that Meta Llama 3.18 billion instruct model, which we, if you recall, on Hugging Face was the one we asked for access to here. So all the details of this model are kind of described here. And in this notebook, that's where we specify the model we want to download. You're able to choose a tokenizer. In this case, and again, a tokenizer, to remind everyone, is what converts the human language to tokens that match the vocabulary of the model. So it typically is like 3 to 4 characters of human language gets translated into one token. And the details of that are determined when that model was trained. So basically, we're just telling it to use the right tokenizer here for that llama model. And there are a few tokens that when the model generates them, how do you know when to stop? How do you know when to stop the model from generating further tokens? And that's what we're defining here. They're kind of like stop characters. Those are specific to the model you're using, and they're defined here. And then the interesting part is here, where we're actually using this Hugging Face LLM library. And we're specifying a lot of the parameters we want the model to use. So we specify the context window, which is, we had that discussion earlier in the slides, sort of the max amount of tokens the model will consider. You can artificially make this smaller here, but it has to be below what the model was designed for or equal to it. So some models have like hundreds of thousands or even order of a million tokens that they support in context. We're going to use a bit over 8,000 here. And then we can also set other parameters like how many new tokens the model is allowed to generate before it stops. So you don't want it to run on, because these are kind of fancy autocomplete, these LLMs. So you want to have some limit on how many new tokens the model can generate. There's this temperature parameter, which is basically the creativity of the model. Like the higher the number, the more more creative. But maybe it results in more likely to hallucinate as well. So this is a parameter we're going to keep it with 0.7 here, but you could play around with it if you run your notebook, and it kind of, and again, if you were actually doing this in a production system, you'd want to have a thorough evaluation framework for your LLM and RAG system, and then you'd try different temperatures and see what produces the best responses, the most accurate responses. We're passing in some of these query wrappers and this boilerplate stuff that we defined earlier. We're passing in the model name we want to download. This is where we specify that we want to use a GPU, not a CPU. So this is using the A100 GPU that we paid for with the Google Cloud Pro that we need to host the model. The stopping IDs, again, we defined those earlier, and then there's another parameter here. Typically, I would just leave this the same as the context length, but this is for your tokenizer, what's the max length that the output can be. So I just set it to be the same as the context window, and then finally, you can change things like the precision of the weights in the model, which can which here we're using float 16, which is half precision. So you can actually shrink the size of the model, but at a cost of performance by changing this. So as we see, we're still downloading. So this kind of gives you a sense of the size of these models and why you have to pay to host them in Google Colab. But we're almost there. We're at chunk 3 of 4 of downloading the llama weights. At this point, are there any questions about the parameters or the setup so far in the chat that we can answer while we finish up the last bits of this download?
There were some fairly general questions. Let's see. So, okay, I'm going to read it out, but I couldn't really answer this one. Does specifying different roles, e.g. user, system, assistant, in the query function of the OpenAI Llama call affect the behavior of the performance?
It it does. Yeah, I mean, so these are pretty standard. So, if you go to like the reg, the llama index documentation, these are kind of standard boilerplate queries that were recommended. So that's why we're using them. If you and basically, so if you these models are basically fancy autocompletes, right? So it generates probabilistically like what's the best next token given the tokens it's you input and it's seen so far and it's generated so far. So the tokens that the model will generate next are really dependent on these roles and the system prompt you provide early on. So we're kind of setting the expectation that all of the tokens the model generates are an autocomplete of it knowing that it is a Q&A assistant and it knowing that it needs to answer questions accurately based on instructions and context, and it knowing that there's a user, the query that you provide is here, and then it knows that, hey, the assistant is going to take over now and do an autocomplete of what the right assistant response is. So this is kind of arbitrary. Like if you change this, you'll get wildly different behavior of your model. You can experiment with it if you run it locally, but this is kind of like a standard boilerplate for this type of example. So it should work for our purposes. But yeah, it's a good question. Okay, so our download's done, and we're able to now use the llama model and take the same questions we asked OpenAI, and we'll pass them in and ask this llama model bundle that's just sitting now in RAM in our GPU in Google Colab. We can put queries into it and get responses from it. So these are the same 5 questions we asked of OpenAI. I'm going to go a little bit quicker. So I know we have about half an hour left. I'm going to go a little bit quicker because you've all seen these questions before through this next section. But we'll point out a few of the qualitative differences between this and the OpenAI example. So this is very similar. We now define a method that, given the LLM we defined up here and downloaded, we can pass in prompts and get the response back. So for example, let's start even before we go into our questions, we can ask, what is the LUX experiment? What's the Large Underground Xenon experiment? We ask this model bundle, and it's able to come back with a good response. So this first sentence here is just a log. It's a benign kind of log for doing this type of inference, so you can ignore it. And then we ask the question, and it comes back and says, hey, Lux, it answers the question correctly, talks about the details of the experiment. It talks about the next generation that which is now has now run and published results. One thing to note is that it cuts off the response in this particular case because the model was still generating text, but it reached that limit that we set up here of the maximum number of new tokens. So it actually just cuts it off. So this kind of shows that, hey, the Llama queries are working correctly, and now we can just run through and generate our responses to the 5 predefined questions we had. So the first one is, let's see. So as you can see, it takes a little bit of time, even on the fancy GPU. We ask, same question, what's the optimal rate between to matching simulation and data? It comes back with a big text block, which qualitatively sounds about right. And in fact, it's pretty smart. It knows that it doesn't have the right information. So if you look at this first block of text, it says, hey, I don't have the specific information about the neutron source rate that provided the optimal match. If you're looking for detailed information, I recommend checking the original paper or the official collaboration publications. And then it says, is there anything else I can help with? The interesting thing is here, since it hasn't reached that 256 character limit we set, the autocomplete from Llama just continues. So it actually starts, another question, which is asks the same question again, and then it answers the same question again. So basically, this autocomplete dynamic could go on indefinitely until we reach the character limit in this case. So in practice, what you might want to do is do some post-processing where you cut at this user token that once you see it. And there's some other options to kind of form the response a little bit more concisely as well. But I think a simple way is just post-processing here. But I think the other thing to note is, okay, so one, it does kind of contextually describe or qualitatively describe the right things, but it even actually, better than OpenAI in this case, knew that it doesn't have the information rather than hallucinating a number, like we saw with OpenAI. The second question that we ask Llama is, let's see. Again, it takes a little bit of time. What's the average electric field? So it actually initially answers the question saying, I don't have the specific information used in the first results from Lux for electric field. But the interesting thing is that it actually just does a run-on response, as we saw earlier. So this first bit of the response makes complete sense, and it ends with, is there anything else I can help you with? And then it continues and eventually starts to hallucinate numbers that are incorrect. So again, you'd probably want to do some post-processing to only select this first bit. And one thing I want to point out here is actually the use here of GPU. So this is one of the reasons why we needed this fancy GPU is we loaded that 16 gigabytes into the GPU RAM to do this inference. So this is why we needed the Collab Pro. And basically, to give a sense of how much it costs, it was $10 for Collab Pro, and it gives you 100 compute units. We're just by using this GPU, we're using almost 9 compute units per hour. So maybe you'd get 10 or 11 hours of hosting this Llama model in your Google Colab notebook. So if you were going to do this for your research group, probably would be better to run it locally on a Mac Mini. That's probably the cheaper option. So the next question is question 3. Um, so we ask about the DD neutron source, and it says it doesn't have specific energy, but in general, um, it eventually figures out that 2.5 MeV is the right response. But again, it's a little bit, we wouldn't maybe need a little bit of post-processing, or maybe we could refine our queries and parameters a little bit more, the boilerplate text a little bit more to get better responses. But basically, it's able to respond with 2.5 MeV, which is right. Question 4, we're now hitting the llama model on our GPU with our fourth query. And we ask about the DD neutron recoil energy spectrum. What's the endpoint and what are the sizes of the scintillation and ionization signals? Here, it just similar to what we saw with OpenAI, it pretty much hallucinates completely. It comes up with quantitative numbers. Qualitatively, it sounds reasonable, but quantitatively, these numbers are completely wrong. So it hallucinates. So you can kind of see there's a different behavior. Sometimes it knows that it doesn't know. Sometimes it hallucinates and talks authoritatively. So you have to be careful when before you trust the output. And the fifth question is shown here about 127. And again, qualitatively, maybe this doesn't really make any sense. The first response is correct. Again, you'd probably want it to stop here and then cut off all of this, the rest of this, autocomplete basically from the LLM. But it knows that it doesn't know, which is a little bit different than what we saw with the OpenAI calls. So I'm going to quickly mount the same things, the same Google Drive here. And we can show how RAG works with Llama Index and on a local Llama model. So we're mounting these here. And one of the slight differences here between OpenAI and the OpenAI example and the Llama example is that we're actually going to choose the embedding model we use. So there's options. In RAG, when you do this step of going from your internal documents, using an embedding model to create embeddings, so going from text to numerical vectors, there's a lot of different options for the embedding model. In the OpenAI example, we just used the default model that the OpenAI API and library chose. In this case, we're actually going to specify the embedding model we want to use, and that is available on Hugging Face. So let me run this. And basically, we're saying download this embedding model from Hugging Face. And similar to Llama, people have publicly published the weights for embedding models, and there's all sorts of evaluations and benchmarks in terms of what makes a good embedding model. But for this, we're going to use this particular one. And there's all the documentation here, and you can see there's lots of variations and different versions and different languages. This one actually supports both Mandarin and English, depending on the version you choose. So basically, we're going to specify the embedding model we want. It's going to download it. This is a lot smaller than the Llama model was. It's only maybe less than it's 66 megabytes. And then we can, in the same way we did for OpenAI, we can create a RAG index, but on the same documents we did before, but in this case, we're actually using an open source or open weight embedding model to create the vector embeddings. So this will take a minute or so, as we saw earlier. And we want to see that we're able to get, now that we have the RAG system set up, we want to see that we're able to get better responses using our local LLM and our local embedding model running in our Google Colab environment. So we're gonna, define a query RAG methods in the same way we did before. We're gonna, in the same way we did before, select the top 5 most relevant responses. And you can see now, now that we have the RAG set up and we've provided the right information, the responses are much more concise and they're quantitatively correct. So basically, if you remember, it kind of had it completely wrong. It said it did not know. It got the wrong answer before the RAG. Now the Llama open source model with the RAG system is able to respond with the right neutron source rate, which is 2.6 times 10 to the 6. And the interesting thing is if we go back to our OpenAI model with RAG, we see quantitatively it's giving the same answer because that's actually the correct answer from the text. So we've kind of reproduced it now with a completely separate LLM. So question 2 is shown here. Let's see if before, it couldn't answer with Llama. And here we see it does get the right answer. Again, with OpenAI, we saw after we used RAG, it was 180 volts per centimeter. That's what we get here. Interestingly, the Llama model continues to run on and do this autocomplete for the rest of the response. So again, you'd probably want some post-processing to cut this off and only have the initial response, which in this case is correct both qualitatively and quantitatively. The next one, let's see if it does better. So this is kind of cool, which is, so we ask, what's the mean energy of neutrons produced? In this case, it gives a really great answer that's very specific to the papers we provided, which is the mean energy is approximately 2.45 MeV, which is right. And is the same thing that I think the OpenAI, if you recall, provided. But it also elaborates further with a really specific quantitative numbers from our papers that we provided, and provides a few different experimental results from the papers. So it says, hey, this value is in agreement with the theoretical expectation. And the measured mean energy from target orientation A and B is measured to be 2.41 with some errors, some uncertainties, and 2.426 with some uncertainties, respectively. So in one of those papers we provided to our RAG system, we actually measured experimentally the neutron energy and quantified the uncertainty, and the model's actually able to pull that out and it reports it here for us. And then it shows that, hey, these are consistent with the mean energy of 2.45. So it's able to really provide that quantitative domain-specific information that we provided to it via papers in the RAG.
James?
Yep.
How do you think it actually managed to make this statement consistent with the expected mean energy? Is it just reiterating what was said in the paper, or is it actually using some more general ability to look at numbers with errors and talk about consistency?
So in this case, I expect that it is using the information. This is a great question, but I expect that it's using the information that's available in the paper, because the paper does say the experimental results are consistent with the expected mean energy. But I would, even if the paper didn't say that, I expect that some of the more advanced models, definitely like the OpenAI, the O1 model, maybe you could get Llama to do it too here. It would be able to do this type of comparison likely. where it if you gave it an experimental result and the theoretical, and there was some uncertainty on the experiment, and said, "Hey, are these consistent?" It would be able to do that type of reasoning. The current models definitely would be able to.
Uh, Thanks.
Yep. And then we can do question 4 here. And let's see. So what is this was the energy at the endpoint, which again, it couldn't answer earlier. And then what is the size of the S1 and S2? So it does an okay job on that first question where it says it returns 74 kVNR, which, as you recall, was the same thing that we saw from OpenAI. Uh, if you recall, the OpenAI hallucinated some weird results for the size of the S1 and S2 signals. We see that Llama also did not do a great job here. It says that they're consistent, but it doesn't give quantitative details, and it's not great on that follow-up question. So maybe there isn't the right context, or maybe you need to tune your RAG a little bit better to answer those questions in practice, if you wanted to productionalize this. So this is again, one of the these RAG systems and LLMs, you always have to be kind of skeptical of the output. Question 5. Let's see. So this is the one that we know, similar to last time. We don't have to go through it all, but we know that the Xenon 127 information was not available in the papers in that initial RAG index we set up. So just like with the OpenAI example. And again, similar to what we saw with OpenAI, there's something's hallucinated here. It gives the wrong quantitative value. It's mixing electron recoil and nuclear recoil here. So this is a case where it really doesn't understand the physics, and it's just pulling information and combining it in a way that doesn't make sense both qualitatively or quantitatively. We can do the same thing in terms of looking at the source nodes. We've already seen that. And then we can do the same trick where we add more documents and get the right answer for that. I'm just going to run all the cells here because we have maybe 10 minutes. And I want to go back to our exercise. But basically, you're able to add more documents, the other theses as you do with OpenAI, and get a good response with Llama. So at this point, hopefully some folks have been able to run let's see. Run the last query. So in the final 10 minutes as this runs, let's go back to that OpenAI notebook. And there was that exercise at the bottom where if you followed along in that first notebook and got all the way to the end, you should be able to run it and get an answer. And the question was, what was the lowest energy of the charge yield measurement achieved with the 2016 calibration data? And then how much lower energy was this than the 2013 charge yield result? So this is kind of a both quantitative and qualitatively challenging question that relies on all the data we pulled into our RAG. So I'm going to look and see. We do have a few responses here. And so I'll paste them in here. Let's see. I'm just looking through the Google Sheet for some examples of correct answers. Let's see. Okay. So let's see. Okay, so we did get a few folks that made it to the end. Let's see. I'm just trying to copy and paste these out. Okay, so here are two responses. I'm going to put them in here from folks that answered. So the first one was someone with the email. This is their email, and I'm not going to paste the full domain, but basically they were able to. Here was the response they got. Add comment. There we go. And the next, and someone else with the identifier, this identifier was able to get a response. I'm just going to paste a few of the folks that got it, because I think it's cool that folks were able to do this. And we can compare responses across the different examples. So I see a third, so maybe I'll stop here. Okay, so there were three folks. There we go. So there were three folks. Here are their usernames from the form and their responses that they paste in, and you can see the lowest QY measurement achieved with the DD106 was 0.27 kVNR, or the 2016 data, and this results in an improvement of more than a factor of 2 compared to the 2013 Lux result, which had a lowest measured deposited energy of 0.7 kV. And then I see the next one, which is interesting because it's a slightly different response, right? So here it says it gets it right again. So this is right. The lowest energy of the 2016 data was 0.27 kVNR. In this case, though, it doesn't talk about it's a factor of 2. It talks about it being a 0.43 kVNR lower than the 0.7 kV result from 2013. So this kind of shows I think, Rick, to your question earlier, it kind of shows the reasoning capability, where in one, the model is thinking in terms of, hey, this is better than a factor of 2 improvement, going from 0.7 to 0.27. And in the second, it is actually thinking in terms of subtraction. So basically, it does have a conceptual understanding and reasoning about these numbers. And then the third response I see is very similar, and it talked about a factor of 2. So I'm going to run the query and see what I get. And presumably, hopefully this notebook is still running. I should get something similar. Yep. So the lowest QI measurement achieved was 0.27, which is a factor of 2 improvement compared to the 2013 Lux QI result, which had a measured energy of 0.7. So as you can see, all of these responses are consistent with each other across everyone that ran it. So congrats to the folks that submitted in the forum and went all the way through the notebook. And this is a kind of a cool demonstration of the reasoning capabilities, getting things quantitatively right, and using the domain expertise and information provided by the papers we loaded into our RAG. And just briefly, so we're at the end of the notebooks here. So just briefly, I'm going to share the results. Showing the actual physics results from this final query. So here is a plot from the Dongxing Wang PhD thesis that we loaded into the RAG. And basically there's some tables with the data. So if you recall, all of the responses from our that we just did, and all the folks that got it right in the form had an energy of 2.27, which was right. So it found this and found that this was the lowest energy. And it also compared, so it was comparing this blue point at 0.27, and it also found in the text the X value of this red point, which was the 0.7, which is also correct. So basically it was comparing the energy here of this lowest blue with the energy of this lowest red, and it pulled those values out of the text, and it was able to share them with us. So quite cool if you're interested in answering questions about your physics, that are domain specific from your physics work. So I know we're very close to the end of the session, and pretty much right on time. So there's 3 minutes left. I wanted to save some time in case any of you have any final questions or comments.
So let's see, the most recent questions. There was can we specify the word limit in the questions, like approximately 150 words in both of these models, Llama and OpenAI, when using the RAG feature? Will it still work?
So you can, yeah. I mean, in Llama, there was a limit. The output limit we did set to 256 tokens, I believe. But that's variable. There are other ways of choosing the amount of output you want, and those are parameters that you can play around with. And it's probably also possible to provide in your boilerplate text like additional information about how concise or not you want the model to be. So you could probably say things like be concise, don't add too many unnecessary adjectives, things like that, and qualitatively change the output based on your system prompt you provide.
Right. Excellent. Okay. We had a very general question a while back, which was asking where did the hallucinations come from? I know you touched on that before. If you want, you could touch on that again, just briefly, obviously.
Yep. Yeah. So these models are one thing I'd refer you to is that earlier in the slides, I said, hey, if you want to go into the foundations of LLMs and how they work and how they're trained, there are a few resources. Definitely, there's a lot to learn there about it. But basically, you can kind of think of them as really fancy autocompletes, where they generate subsequent tokens based on the tokens they've already seen and the tokens they've generated so far. So it's basically saying, given everything I know from my training data about the statistical properties, what of the next token, what's the most likely next token going to be? And there's some non-determinism in that, that's built into the models because there's a probability distribution for what the next token should be. And basically that's where you get this randomness, where if you ask the same question over and over, you can get different answers. You can see different hallucinations. So basically, it's a fancy autocomplete that can complete things that qualitatively sound right, but in our case, we were getting a lot of quantitative hallucinations because it knew a number should come there, but it was making up numbers. So that's where they're coming from.
But all right. We're at the half hour. We should draw to a close there. James, I just want to say thank you so very much. I've been over the last couple of years in many conversations concerning this type of work. Watching you, as you were developing the module and the discussions, and just how successfully, I think, certainly to me, it conveys what is possible, at a single user sort of experimentation level, but also what, that one has to develop one has to spend a fair amount of time with these systems to begin to understand how, the level to which we can use them and we're not. We also, going to need deeper and deeper pockets if we keep pushing up the compute. Yeah, that we're going to have to understand how to keep these things as efficient as possible. But no, thank you again, James. It's great working with you again.
Yep. Yeah, great working with you and Wen and everyone else. And thanks everyone in the audience, and thanks for the invite to present today.
Okay. Thank you, everybody. Okay, so we meet again tomorrow at 10 a.m. Eastern Standard Time in the USA. Really appreciate all the great questions. And thank you to many of you who've been running the notebooks alongside. Okay, see everybody tomorrow, Thursday, 10 a.m. Eastern. Thank you.